think he's joining right now, so
Okay.
yeah,
Awesome.
I'll let you kick off.
Yeah, I'm here.
Sure. I think you can get started.
Yeah, awesome. Hey everyone, thanks for joining our training Blitz series. I think today we are covering Iceberg, which was one of the requested topics previously. Thanks all for joining. We're joined by Jay. I'll let him introduce himself, and we'll be happy to give an overview and take any questions as we go along. Jay, feel free to take over.
Sure. Thanks. Hi, everybody. I'm Jay Askew. I am a data analytics customer engineer here at Google. And so I work with various accounts. Spend most of my time working on BigQuery, but when you're building a lakehouse, Iceberg becomes a very common topic. So we'll be doing a talk today about Iceberg. Let's see here. I need to share my screen. Give me 1 second. I've got too many windows open, so I got to find the right window. Okay, are y'all just seeing the slide now? Okay, good.
Yes, sir.
All righty. Okay, so are we ready to begin? We waiting on anybody else? I'm going to take that as yes.
No, we can start.
Okay, all right. Thanks, Wayne. All right, so today we're going to have a talk about Iceberg and BigQuery. We'll talk a little bit about how it works, how it's supported in BigQuery, and what it is. I'm going to start off. Here's the agenda. I changed the agenda a bit from what was advertised in the original invite that went out. I think the flow is a little bit better. You talk about Iceberg, and then if you're talking about Iceberg, you're clearly probably talking about lake houses, and then if you're talking about doing Iceberg and lake houses at Google, then you're talking about doing it with BigQuery and a product offering we call Big Lake. So I felt like the order would change, and I won't be doing a demo today, even though it originally said this is more of something that's easier to talk about conceptually. A demo would effectively be me just creating a Big Lake Iceberg table and then turn around running a query on it. So it's not really all that impressive. I think it's more important to talk about the concepts about how Iceberg works and why we do it and those sort of things. But in the reference slide, there is documentation, or there is a link to the documentation that tells you how to create the table. And so if any of you ever have any trouble, my email address, of course, is on the invite. I can give it to you before we end today, and you can always send me questions to answer if you have any trouble. And I know I'm working with some of you who are interested in this very topic. So we're going to talk about Iceberg, lake houses, and some BigQuery at the end. So there's definitely a shifting sort of paradigm in how customers store and analyze data. I've been doing data analytics. I've been doing databases and data in general for quite some time. And of course, it started out with data warehouses. You would have sort of this very structured schema, and many customers would just use a typical, what we call an SMP system, which is just to say it was just a box with multiple processors in it. And they would use it for a data warehouse purpose, but they would use a data warehouse schema design. So they would create a star snowflake type schema. They would denormalize it, and then the industry sort of evolved, and data warehouses got bigger, and so we created more appliance style that scaled out and had multiple nodes, kind of similar to how Hadoop did with big data. You would have a head node and multiple worker nodes. And then as data grows, I think I read a statistic the other day while I was sort of polishing the slides that data is expected to double every 2 years. Right now is the current pace. And so as data grows, a lot more of that data is becoming unstructured. So then customers move to data lakes, and they wanted to look at data that was unstructured, that wouldn't easily fit inside a database, inside a structure, a table type structure. And this was great for ML type data scientists and stuff like that. But getting insights out of it and building those into business insights and things in the typical style that you would do with a data warehouse and BI tools, there was a lot of friction. And so those were the two that you had. And so to marry those two together, then we see lake houses coming out, which really takes the best of both worlds and hits the name warehouse, data lake, lake house. They try to take the best of both worlds. The good things, and we'll talk about this a little bit later, the good things that came out of structure, not everything's bad, and then the good things that the data lake has to offer, and really capitalize on the best of both. I'm going to start with some what I call foundational terminology. I don't know the background of many of you on the call, so I don't want to assume that you know all of these concepts and these terms. There will be some other terms that we'll talk about that may not be up here. You can stop me and ask me, or I'll try to explain what I'm talking about. But these are the common ones for the stuff that we'll talk about today. And as you do further reading, whether it's in our documentation, there's a pretty good book I can recommend. Anywhere you go, there's actually a good blog post I'm going to recommend that I actually borrowed one of their diagrams to go over and explain how this works. So you'll come across these terms, and some of these terms are again from the old, like ACID and stuff. It's from the old database days. So we'll start with a table format. What is a table format? So a table format is basically just a specification and some implementation that deals with how metadata is going to be managed about data that you have sitting in storage. It's going to dictate data storage, data organization within that table. It's going to, it provides ACID type properties, and it really increases interoperability, because a lot of these are referred to as open data formats, meaning it's an open spec. You can go to apache.org and you can read about everything about how everything I've got here. You can read all this and much more on how Iceberg and the table format works. And you can do that with any of the open table formats. So some other examples of table formats besides Iceberg is Hootie and Delta Lake. And I remember when Delta Lake first came out, and it was a big competitor to where I was working at the time with data warehouses, and they were trying to introduce transactional semantics and stuff that you could do over a data lake using a Delta Lake table format, which comes from Databricks. So that's pretty much what we're talking about when we talk about Iceberg. We're talking about a table format. Underneath the table format, you have file formats, and those are generally also open standards, or they're going to be open standards in this open table format. They're not going to be proprietary. Whereas if you have, even if you have BigQuery native storage, we call our file format that we put in there capacitor. So it's more of an internal name, but if anybody ever says that, that is the columnar store that BigQuery uses. I come from, I've been at, I didn't say this in my introduction, I've been at Google for about 4 years. I come from Microsoft. I worked for a long time on SQL Server. They have their own proprietary format, and they include columnar indexes inside SQL Server. So what we mean when we talk about a columnar databases are really good, or columnar storage, I should say, which BigQuery uses and Iceberg uses. Iceberg can actually use both. Columnar storage has you store, if you think of a table in your mind, it has you store all the values that are in a column. So going vertical down a result set or a table, store all those together in storage. And this is great for two reasons. So if you're doing an analytical workload, everything's going to be close together. You're going to reduce I/O, and I/O is usually one of the most expensive things you're going to do in any database system. I spent a lot of time looking at I/O when back in my days as a performance engineer for SQL Server. So you're trying to reduce the I/O, and then on top of that, because you're storing like data types together, you get a added benefit that the compression's really great, because you have a lot of repeated values that look the same to it. So you get great compression, you're storing everything you need, and again, that's good for analytics, because in analytics, you're doing these sort of aggregation queries. You're saying, you know, give me the sum or the average of this number, this sales in this region, or something like that. So you got to go get one column out of everything. You're not interested in everything that might be in that row. Then row-oriented is more of your transactional. Everything with that particular entry you're interested in, like a shopping cart or a product catalog. You're interested in all the things that are in that row, or certainly a lot of them. And those formats are Avro, CSV, that type of stuff, and regular, what we think of as regular RDBMSs that store in a row-oriented format. You're going to hear us talk about a catalog. That is sort of the entry point into Iceberg. It is a register, could be a database, could be a file. Implementation kind of doesn't matter for our talk today, but in the terms of Iceberg, it's going to contain the pointer to the first metadata file. And so a chain, or really what would look like an upside down tree of metadata files, is how Iceberg manages the location of files. All the stuff is stored in files. Some of those are Avro files. And then when you get down to the data files, you get to pick. Parquet is probably the most common. But this is sort of the entry point. This represents the table. And so it can point to, okay, this is where it starts. And as we get into more things like Big Lake, there could be additional information that the system uses to provide you extra services and functionality beyond what the Iceberg spec does. Like, we're going to talk about that when we get to Big Lake, and why Big Lake adds to what you would do if you were to just say, hey, Iceberg's an open spec. We can just go create our own Iceberg lake house. Why do we need to use Big Lake? Why should we let Google do this? And that's because there's going to be added benefits that takes work off of you, but also adds, there's some features that are additional, some very big ones in today's market. I put this one just for coverage. Probably don't need to talk about this. It's basically data about data. Metadata means data about data. And that's what's in all these files, all the way down to the data files, is data describing your data. A lot of it's describing location, but some of it is describing min-max values. It's describing ranges. It's describing data structures, as it says there, characteristics of the data. And so it helps us manage the data, and it helps us get through it. We'll talk about ACID. We talked about that earlier, in a few slides ago, about what is Iceberg. ACID comes originally from RDBMSs, so the ACID properties are listed there. Atomic. So if you have an ACID transaction, it's a guarantee that when you run a transaction, it's atomic. It'll complete altogether or not at all. So it won't partially complete. The database or the data set is left in a consistent valid state. It won't be left where something's half done or not done to one table, not the other. And isolated makes you feel like you're the only person in the database. Transactions do not affect one another. There's different ways that can be handled. And then durability, also implementation for each of these can be done differently in different systems, but durability is a guarantee that once you commit it, once you put it in the database, it's guaranteed to be there. It won't disappear on you. Two more slides on terms. Clustering and partitioning. Clustering is basically just sorting. When we talk about clustering, we're talking about storing something in the sorted order. So BigQuery does clustering on tables. Iceberg has clustering within the files. And partitioning, so whereas clustering is physically sorting the data, partitioning is dividing it up into separate physical structures. If you're dealing with a database, that's typically separate physical tree structures, separate physical indexes, things like that. Here, we're going to have separate groups of files. And so if you think about buckets and you have a bunch of numbered balls, I like this analogy. If you have a bunch of numbered colored balls, and you put all of the red balls in one bucket, you put all the blue balls in a bucket and all the green balls in another bucket, they're partitioned by color because they're in separate buckets. And so when I say that I need you to get the red ball number 4, you can automatically not look at the other 2. That's something we call partition pruning. We know we don't have to look at the other 2 buckets because they contain no red balls. So we can go straight to the bucket that has the balls that we need. And if they're clustered and sorted in order, we probably have a pretty good idea of whether it's at the top or it's at the bottom of the bucket. And finally, optimistic locking. These systems, a lot of analytic systems, but Iceberg, they go for optimistic locking. Optimistic locking basically means that they typically rely on some implementation that checks the version of the record before they make the change to see if it's changed since you issued the command or issued the transaction. Pessimistic locking, which is more common, So optimistic locking assumes that, conflicts are very rare. It's not going to happen because there's an overhead when you take locks. It's a data structure that has to be tracked. It causes, it's a data structure that has to be tracked. Code has to run to go acquire the lock and things like this. And when you're running high performance systems, those costs add up. So optimistic locking just assumes that happens very rarely. We'll just check the record right before we make the change to make sure that that nothing is in flight. And like I said, implementations can vary, but that's the idea behind optimistic locking versus the alternate, which is pessimistic, which is a lot of transactional databases, says, I'm going to take a lock on this record. Even to read it, I may take a lock, so it's not changed out from under me. And certainly if I'm going to change something, I'm going to take an exclusive lock or something like this, so that everybody's aware that I'm making a change right now. Don't read this until I'm done making the change. That's a pessimistic locking, meaning that we assume conflicts are going to happen. And in a high concurrency system, that's probably a reasonable assumption. Most of your analytic systems are not nearly as high currency. I talk to customers about this a lot. You don't expect BigQuery to be a high concurrency system. You don't expect to have 3,000, 4,000 people in there at one time trying to run things. It could support it, but you would have to take that into consideration in your design because of the type of service BigQuery is. It expects you to go in and run massive queries against petabytes, terabytes or petabytes of data. That's what it excels at. It doesn't excel. None of these analytic systems, column store itself is not going to excel at you going and saying, I want to go find this one record. I want to go update this one record. That's really not what these types of systems are designed for. Okay, I'm going to take a pause and take a drink. Any questions on the terminology, let me know. I heard a beep. I don't know if that means anything, but okay. All right, so what is Apache Iceberg? So Apache Iceberg, as we said, is a table format. It's created by Netflix in 2017. The story I've read, I wasn't there, but the story I read is that it was to address issues with Hive. So it provides a structure for data lake houses. I should correct that slide. It provides a structure really for what's used in data lake houses. It could be in a data lake as well, but it marries the benefits of these more structured data warehouses and data lakes. So we see it used most commonly in lake houses. Ironically, right now here at Google, we're going through some academy training on open lake houses with Big Lake and BigQuery. So we have an internal training going on, and that was the first thing they said the first day. What they see from the engineering side, Iceberg is pretty much taking the lead, especially in lake houses. That's why you're going to see that a lot of Big Lake, we have special tables that say Iceberg tables, and the older, I don't want to call them legacy, but the Delta Lakes and the Hootie, we don't have a table specifically that says, we have external tables for that purpose, but we don't have Big Lake tables, or we call them Big Lake Iceberg tables. You're going to see they've been doing some name changes, so all of us here at Google might stumble a little when we're saying the names because you get an idea and then you let marketing get a hold of it and it gets confusing. So supporting ACID properties, these are the things that Apache Iceberg brings. It has improvements over Hive. So Hive is a framework, a compute framework, if you will, inside in the Apache organization or consortium, whatever they call themselves. What Hive does is Hive simply lets you take and write SQL statements. The simplest way I think to think about it is it lets you take and write SQL statements, and it converts those to MapReduce jobs to do what old traditional Hadoop and HDFS did with MapReduce. So for people who don't want to write Java files that do MapReduce and implement a mapper and a reducer and stuff like that, they came up with Hive, which was, if I'm not mistaken, I think it was actually Facebook that came up with it, but I could be wrong on that. So it was a system to go through these very, very large data sets where you need to do analytics, where on the other side, relational databases, traditional transactional relational databases, even though they got big, they hit limits for two reasons, because they were generally tightly coupled in a single SMP system. So they solved that by breaking them out into these appliances that had multiple machines, but also all the overhead, the locking, and all the stuff that goes through to give you that integrity in these things that we talked about They don't do very well. The very design of them, they don't do very well in large analytics cases. Like you can certainly do. I've seen customers with hundreds of gigs in SQL Server, a couple of terabytes, but a couple of petabytes, no. I personally have never seen that. So Hive basically came around the time that also I would say cloud storage was getting big. So they had to adapt it to cloud storage. I remember us doing that back at Azure. So it treats directories as tables is the first thing it does. And so as it does that, as the data set grows and grows and grows, you have this problem with it getting slower and slower because it has to read and process through all these files. It doesn't have nearly as effective pruning. It has pruning, it has partitioning, but it's not as effective as what we're going to talk about in Iceberg because Iceberg handles it at the file level, not at the directory level. And it also treated, because of when it started, it treated everything as a hierarchical file system. So in other words, it offloaded some of the work to the file system. And a hierarchical file system like NTFS on Windows basically has a file table that operates as an index into the storage. And cloud storage systems don't work that way. They're effectively key value pairs, and it's a very flat naming space. When you create directories on regular object storage, that's just part of the name. There really isn't a directory there. It's just part of the name, and the connectors and the system understands that that's part of the name. So Hive had problems as it got bigger and data sets got larger and larger. And so that's when they came up with Iceberg. So Iceberg has the ACID transactions. It brought in, as I've said a couple of times already, and I'll say again and again, it started bringing in those things that people like that were pushing the limits of big data warehouses and they were used to in regular, let's call them schema-bound systems, schema on write. But then also the stuff that we liked about data lakes and the stuff that we liked about big data systems like Hive, where it was also a little less strict with the schema evolution. Hidden partitions is talking about the fact that it can do partitioning. You don't have to worry about it. And then this concept of time travel, where that's basically in Iceberg, we're going to talk about in a couple of slides about snapshots. And so time travel just gives you the ability to go back in time and give it what, here at Google, we call it a time decorator, to say, I want to query this table as of this time. And it knows to go back and say, well, this is what this record looked like at this time. And so we have that also in BigQuery. Because BigQuery is a managed service, specifically the native side. When I say native BigQuery, I mean BigQuery's own native storage, not Iceberg. We put a limit on how far back you can do time travel. I think the limit is it's 21 days or less. I'd have to look. The default 7 days, but time travel is become a very common feature in these large analytic systems. All right, so let's talk a little bit about how Hive works. I want to give credit. I'm going to send the slide deck out. On the references slide, the first link is where I sort of snagged or borrowed this image because this guy did a very good job. It's a blog post he wrote on Medium. I'd come across it before, and I thought it did a very good job. He does a very good job of explaining all this stuff, so you can take a look at that, and it'll go into more depth than what I'm going to go into. But basically, this is the graph that he took off the Apache org website for the table spec for Iceberg, and then he annotated it. So I'm not going to sit and break this down too much because it gets to be a bit tedious. But basically, we talked about the catalog, okay? And with the catalog, what you have underneath it is a series of metadata files. The first one's called a metadata file, and it contains pointers. All these files basically contain pointers. These files are immutable. And so what we mean by immutable is that the files don't change. We create new copies of the files with the changes. We leave the old files in place. And that's a common thing for all these big data systems. It's just the way these things operate. So, but one of the benefits of that, of course, is it makes snapshotting very easy because now what I'm going to do is I'm going to go into these metadata files. And when I make changes, I'm just going to adjust a series of pointers to point to the new file. And I'm going to leave the old one in place, and there's my snapshot. As long as I maintain a list of pointers that are associated with that, I can get back in time to a different snapshot of the data. So the metadata file contains the list of those snapshots. So the top one says, hey, this is your table. Here's the metadata file for it. Then And there's a little bit more to it, but I'm going to simplify it for what its core functionality is. Then the metadata file says, well, I've got a list of snapshots, and which snapshot you going? Okay, you're going to this one. Then it goes to a manifest list that contains a list of pointers to manifest files, and manifest files have a list of pointers to data files, and those data files are going to be your Parquet, Avro, and so on. So you can see if we just adjust these pointers and we keep old manifest list around, which is effectively where the snapshot is. So I can have a manifest that says, hey, I've got these list of pointers to all the manifest files, and those are the ones that have the pointers to the actual data. That contains a set, and that's my snapshot. And I can keep that around, and I can get back to it by traversing through with a time decorator. So if we look at it from another angle on how these changes are made, this slide's basically saying we create the table, we get the metadata file. Then as we start inserting data, we create that manifest list. We've created our first snapshot. Then we create manifest list, then we create manifest files. The naming convention is similar, so it gets very confusing when you try to explain it. But we create the manifest files, which are then eventually we're going to create the data files. The point of this slide, I think, is that as we, in this example, they're doing an insert, so we create the files, and then they're doing a delete, and many times an update is treated in many systems as just a delete of the old and an insert of the new. So you do a delete, and so really what you're going to do is you're going to adjust the pointers. You're going to do, there's two mechanisms that you can do here, and I know I've discussed this with some of your teams there at DMB. We're going to talk about that on the next slide, but effectively you're creating a new file, and you're just adjusting pointers on hey, who's the current file, who's the current version, and then the older manifests that implement the snapshot keep track of the old one. Those two mechanisms are something called copy on write and merge on read. So copy on write, if you imagine that you have a data file that you need to change, we said we're not going to change the file. What we're going to do is we're going to copy what's in that file with the changes put in place into a whole new file. Okay, so as you can imagine, and we'll leave the old file in place again, giving us our time travel capability. As you can imagine, if every time I make a write, I have to completely recopy that data file, then that can get expensive for write operations. That'll slow down write operations considerably. So you need to consider the update frequency, the insert frequency. Doing batch loading may not be a big deal, but how often are you updating and changing data is probably a bigger deal. Then the merge on read it takes a different approach where it says, I'm going to write the changes, and we have two ways of doing this. We have what we call position deletes and inequality deletes, where an equality delete says, I'm going to record the exact criteria that you use to delete it, and the position delete says, I'm just going to record where that record was. And so what it does is, then when you go to do the read, it's going to take the original file, and it's going to take the, let's call it a delta file or a delete file. It's going to take that file, and it's going to arrive at the current state of the data from those two files. It's going to merge the changes on each read. So there's not necessarily a right or wrong. It depends on your workload. If you're going to do a lot of reading, copy on write may be better because the read operations won't go through the cost of doing the merge every time. And if you do a ton of writing, then the merge on read may be better. You're probably going to have to figure out what the balance is there. This can create, I think I didn't put it in the slide, but this can create so there's a couple of problems here. There is concerns. Obviously, this design leads to metadata bloat, some people will call it, where you're going to have more and more manifest files, manifest list files as you get more and more snapshots. And you might have more and more delete files or more copies. So the system sort of gets larger and larger because the data is growing. And if you make a lot of small changes, that's what's usually referred to as the small files problem. Because remember, when we make a change, we go create a new file. We don't make that small change in the file, so a whole new file gets created. And if it's the merge on read, we're just creating the changes, then you're creating a lot of small files, and the small files problem. This is why Iceberg has methods to do compaction and has methods to do garbage cleanup, to basically go through and remove these, call them tombstone records or records that are no longer valid, or to take a bunch of small files and compress them down into a larger file with an optimal file size. How that works is a little bit beyond what we're talking about today, but what I want to point out is that if you're just doing straight open source Apache, or you're doing something like that where you're managing it yourself, you're going to have to figure out what the schedule is and how to implement that. And chances are the compute engine that you choose is probably going to help. That's the case with Big Lake. If you do a Big Lake managed table, it's going to take care of all that for you. It's going to pick the optimized file size. It's going to recluster, make sure the data is sorted so that it reads quickly. It's going to handle all that. And that's one of the benefits of using something like Big Lake. And then we're going to talk about a couple of other benefits that I think makes it very much worthwhile. You're going to get this, so I'm not going to read this, but this is basically a comparison between Iceberg, Delta Lake, and Hootie, what those files are for. It may be so small that you probably can't read it. I'm here in front of it and I'm having a hard time. So, but it's just a comparison chart, so you know that these are some of the other popular open table formats. So that sort of gets through a quick overview of Iceberg. I'll take a break if anybody has questions, and then let's talk a little bit about lake houses. Okay, so starting off here with a little bit of I call it a sales slide. Open lake houses. So the concept of open is good because everybody likes open, because I like the second one. It sort of prevents vendor lock-in. One of the big promises of having an open table format on top of just the never mind the lake house, having the open table format is more and more engines. You know, probably in my world, two of the most common obviously is using BigQuery, although you can also use Postgres or AlloyDB. But for analytics work, BigQuery and using Spark. So we're moving to a world, and I want to point this out a little bit later. We're moving to a world where you have more choice, and more choice is good. More choice brings down cost, which we're talking about. It's also going to bring down complexity as well. And we'll talk a little bit more about that in a minute. And we're going to talk about the migration hurdles. If I can export data out of a current system into a common format, clearly that's easier than if I have to migrate it out and then put it into another proprietary format and then go through all that again. Sort of the goal that I think people are hoping for, the holy grail, if you will, is that we're getting this data into an open format where multiple engines can read it. Everything knows how to read and understands what this Iceberg table format is. So you pick your compute engine, you pick your execution engine, and we don't have to constantly go through this thing. Well, we upgraded. You know, if you get an upgrade in Spark and it gets features to make it faster, like an advanced runtime or optimizations, or you go to a different execution engine, as long as it knows how to read your open format, you don't have to do anything with the data. You don't have to migrate and create ETL pipelines to move the data to another system, which we've had to do in the past. So that's sort of the short of why open lake houses and what they do. Those two things, what I just described, plus what I described earlier, which is bringing together the best of both of these two worlds, which I started to talk with, which is you had the data warehouse. And when you had the data warehouse, I like to tell customers, and this is kind of what they're talking about there in that sort of middle shaded band, the data warehouse was always good at answering questions that you knew to ask. You know, if it was financials, if it was whatever it was that senior leadership or management or Wall Street or whoever you need to answer questions for about the business procurement, you knew to ask them, and the data was in there. The data was curated for that specific, and that's the best way to think of the data warehouse. It's curated data. The data lake was larger. More of an exploratory nature where you would turn loose data scientists, and it was more unstructured. And I always told customers it was where you kept the data that answered questions that you didn't yet know to ask, and that you will figure out later, and you'll say, oh, if only we had that data from back in so-and-so, we could probably answer this question, because we need, say, data over a 10-year, 20-year period, and that raw data would have had the answer. You kind of lose something many times when you curate data, because in the process of curation, you throw away something you think is not valuable, or you aggregate it and you lose a level of detail to get to the answer because they want the data warehouse to run fast. They don't want the data warehouse to go through billions of rows of data. So historically, data lakes, so data lakes are perceived to have limitless compute and storage. So that was the horizontal scale issue that I talked about. And they handled unstructured data very well. And then on the data warehouse side, you had more of the structured cleansed view. Everybody's very well aware of that. Granular access control, ACID compliance, business intelligence. So you can kind of see the goal here is that the Lakehouse brings those bolded terms together and tries to, again, take the benefit and take the best of both worlds and put them into a common platform, hopefully with an open table format and an open data format that will prevent you from having to do certainly as many migrations and hopefully almost none moving forward. And so the point I wanted to make here when I saw this slide, I underlined separation of storage and compute. So in the old days when you had a database server sitting on-prem, storage and compute were tightly coupled together. They were either in the same box, and the box would only support, in the backplane, it would only support so many hard drives being inserted or whatnot. And then we moved to SANs that would let you expand the storage, but still at that time, it could be even a limitation of the operating system would only support so much storage. And now we went into cloud and let things obviously scale much larger because you could scale horizontally. But the big thing it also did was it decoupled compute and storage. Storage and all the major platforms obviously is completely separate from the compute, and the decoupling lets you scale them independently. Do you have a big compute situation? I worked on HPC clusters for a while. Do you need a tremendous amount of compute power? And you'll typically in that scenario have a smaller set of data, and you'll probably produce big data from running models in an HPC type system. Or do you not necessarily need to compute as much as you need large data? You have big data. So that decoupling really helped a lot and helped free up customers' ability to scale where it was needed. But the thing about what the open table format specifically is helping do is it's taking that decoupling even further, because now not only can you scale them independently, now you're able to choose what compute layer you want. We already mentioned you can do this with Spark, you can do this with BigQuery, and of course the goal there is that you can do it with both. A team can pick which one, is a team more inclined to write traditional code in something like Python, something that's more robust, something that may have better handling of conditional logic or something like that than what SQL might have? Or are they very skilled in SQL Server or the SQL language, I should say? And they're very comfortable with working with things as data sets, and they're very comfortable with that type of thing. And what do each one of those ecosystems offer, which is, you see the term there in orange, analytics lakehouse. I'm going to point out what we mean there in just a second. But again, open table format. Now, if we can have these multiple compute systems, instead of saying, oh, well, this system does better, let's push the data over there. That was the biggest complaint I heard from one of my customers I supported several years ago was the need to move data around. So we're trying to get away from the need to move data around, have multiple copies of the data. And again, if you have that, obviously you're going to have reduced complexity. You're going to have reduced cost, and hopefully make things simpler from not having multiple copies of the data, not having these ETL pipelines that you have to work with. And this is really just, this slide's just stating the same thing that I just said. So I can probably kind of skip right through this one. Open format, lower cost. So in context of a lakehouse architecture, so if we talk about, on the left, it's talking about governance. That would be a different call. We have governance tools. Probably the most common one there that you guys might be interested in at some point is going to be Dataplex. So that's going to also bring up Dataplex Universal Catalog. That is different from the Iceberg catalog. So think of Metastores as, hey, I'm just tracking all the data that's in your lakehouse. A universal catalog like that is for human consumption. It is for cataloging your data assets, period, throughout the entire enterprise, creating stewards, making a searchable experience so that people can go say, hey, surely we have this data somewhere. You would go to that type of catalog and see if you can find it, who's responsible for maintaining it, and what the usage rights are, and this sort of thing. Data processing on the far right. Of course, the data processing What's going to come up mostly is ETL, data flow, or using data proc, which will be Spark and things like this. You can do data processing inside of BigQuery with something like data form. Analytics Hub, that's more of a sharing exchange type concept. And then ingestion. The one where we're focused today is right here in the middle. So this is the data storage layer. That is where our Iceberg tables are going to sit. Specifically, they're going to sit in those two blocks right there. And we're going to talk more about multi-cloud storage, which, again, now we're going to start seeing, well, why Big Lake? If I'm going to build a data lake, why is Big Lake? And again, Big Lake is is our name of choice for that is BigQuery doing a lakehouse. Just think of it that way. It's BigQuery doing a lakehouse. So we're going to get into now with Big Lake why it is has some special things and unique things to offer for building a lakehouse. So now we'll get into the Big Lake, and I will pause again to see if there's any questions around lakehouse. All right, moving on.
Yeah, I mean, sorry.
Yeah.
Yeah, so quite a few questions. So first thing, a great presentation. So have questions on the table metadata architecture for whatever file we have. So how does Iceberg's metadata layer scale with billions of partition data if we have?
So when you talk about scale, so on the one hand, we I guess you have to take a couple of the concepts and tell me if this answers your question. You have to take a couple of the concepts that maybe I didn't type together for you exactly. In those, I could probably fly back through here and get to the right slide. Hang on one second. In those slides, you're going to see in the manifest list and the manifest file. So when you say scale, you could think of scale in terms of I need to have storage big enough to handle it, and that gets into the file system. So that gets it. So we can talk about scale in terms of size and maintaining size, and so that's where you're going to have a plan, or you're going to have to use again Big Lake for us to help you do compaction and garbage collection. Compaction is not just about, because if you're keeping a lot of snapshots, then okay, well, I'm keeping a lot of snapshots, so I need all that data. There's really no garbage to be collected, but the compaction will take these small files and get them down to, based on the size of your data set, at least Big Lake, based on the size of your data set, and that's going to be in one of my final slides, it'll pick an optimal file size. So on scale on this size, on that side, there's that. Scale on the side of of performance, of saying, okay, we've got billions of files. Obviously, there's going to be several optimizations, but the two key ones in BigQuery does this for its native storage. It should have partitioning coming. I don't think it's there yet. It has clustering. That's where these two options come in. So as we come into the metadata files, okay, when you get to the manifest file, the manifest list, the manifest list will contain additional metadata that'll let us do pruning. So it comes down to pruning. So the manifest list is going to say, hey, I know what's in the partitions beneath me, which is tracked by the manifest file. I wish they came up with like vastly different names, because it makes it confusing when they sound so similar. So I'm going to genericize this. Each of these files at their different layer, depending on what's just beneath them, they have additional metadata that helps you do pruning. They say, hey, this is the upper and lower bound of the data beneath me. And so remember the bucket problem, or not problem, but example. At a partition level, it has upper and lower bounds. It can say, hey, what you're looking for. And remember, it can do some of this automatically. That's what they mean by hidden partitioning. You don't have to explicitly do it like you would do in an old school database where you say, hey, I'm creating a partition. Here's a partition key. And hey, all of you be sure that you're querying on the partition key. So what it can do is it can say, I already know that you're looking for red balls. I don't need to look at the other two buckets at all. I know you're looking for red balls, so I can just go in this bucket. Now let's go down another layer. And with clustering is needed for this. When I get down to the manifest file layer, it does the same concept, but it's looking at the data files, and it has min-max values. So it says, I know what number you're looking for. I don't need to look at all these files. They couldn't possibly contain what you want, because again, I make sure the database is consistent. That's one of the ACID properties. And I know that these files don't have it. I know I need to look through these 4 files. So it becomes
Yeah,
a
it's
traversal
correct.
to the metadata.
So yeah, that's correct for the read wise. But let's say I have a petabytes of file, right? And I don't want to create a big file like 2 GB, 5 GB, right? I want to have 500 MB for a petabytes of data. So in that case, I'll be having a lot of file in my backend storage, right? Along with the Iceberg metadata. Because if we have a millions of file, that needs to track in the metadata somewhere, right?
Right. We talked about
So-
metadata bloat. That's right.
Yes. So when I want to read that data through Spark or maybe Big Lake or BigQuery, so does it take some time to parse all the metadata or a query parser kind of thing? Because we have a lot of metadata. Metadata itself is maybe a 10 GB or 5. I don't know, but I'm just giving a number like maybe 10 GB data. I have a metadata.
Yeah. So first, I think nowadays, certainly when you're working with a product like BigQuery, or even if you're doing it in Spark. All right, so I got to speed through some of this. So let me take my best shot, and you feel free to email me if you want to continue the conversation. First off, 10 GB is not big data. It's nowhere near big data for either Spark or BigQuery, but I get that's not necessarily your point. There would come a point, so the size and the number of files would be a function of how long it takes. None of these are analytic systems. None of these systems are expected to return in sub-second return times. That's if you're looking for, I've had customers looking for that. That's not a guarantee that any analytic system should be making. That's not what it's for. So it will be a function of how much metadata do I have to go through. Yes, you're correct. And this is the optimization that Iceberg implements. There could be some more optimizations that I'm unaware of in Big Lake. That would probably be something I'd have to ask engineering, to be honest with you. I know they pull more into the catalog, but yeah, you would need optimal file size is something that I know Big Lake does for you. I'm not exactly sure how other platforms do it. If your concern is optimal file size, because I think what you're getting at is if I have a lot of small files, then I got to have a lot more entries and metadata. So I'm doing a trade-off. I have a small file size, but now every read has to go through a mountain of metadata to find it.
Yeah, correct. Concern in the size of
valid
metadata,
thing.
but size of metadata that grows over the time.
Yes, that's very valid, and that's part of what the compaction process will do, is to clean that up. And we pick an optimal file size, and part of that optimal file size, at least for us, is to make sure that the metadata size is correct too. That we're not, every read has to go through some level of metadata, and it's almost like an index. You have to go through these layers, and so if you have to but it should be a vertical traversal for the most part. You're not reading horizontally across every manifest list. So as long as you keep those files reasonable, again, it is going to be
yeah, I mean, because in that case also it has to go through the metadata, even though it has to. Right? So if it grows over the time, then how much is, let's say, the query planner in the Spark or a BigQuery compute side, right? How much time it takes and all.
It's physics. It has to go through the metadata, and keeping optimal file size is one of the things we do for you. Yep.
Okay.
Feel free to email me if you have more specific questions.
Yeah, sure. Just another one again for a Spark compatibility, because let's say if I want to use that Iceberg catalog, which is GCP managed through Spark, I don't want to use Big Lake for that.
Okay.
So what's the compatibility with Spark for this GCP managed Iceberg?
Well, so the GCP managed Iceberg for what we're talking about today is going to be through Big Lake. So if you're not doing it through Big Lake, it's not going to be managed. You're going to have to do it yourself.
Okay, so
I don't work with Spark as much. I can try to get an answer to see if they have an answer. If I don't know that I don't believe they have a managed in our Spark and Dataproc. I don't think they have a managed Metastore for you where they manage it for you. To my knowledge, but I'd have to ask somebody that works in Spark more than I do.
So in that case, we have to use
Big Lake Metastore. You won't have a managed experience in GCP. You'll do it yourself.
Yeah, I mean, Big Lake Metastore, it's fine. So we have to use a Big Lake compute, is it? Because Spark is already our compute engine. So if we go through Big Lake, then we have to use a Big Lake compute.
Let me get through. I'm going to fly through these few slides here, and then I think I don't know if it'll answer your question, but the
Yeah. I mean,
sort of
just
the
the
area that you're
few.
asking questions are is sort of right at the end. And so we'll see if we can get through that. And if you have more questions, then we'll use the rest of the time for that. If not, again, you can email me and I can
Sure.
answer what I can answer. I'll run down what I can run down. I don't do Spark as much as I do BigQuery. So some of the Spark specific things, but they don't have a managed right now. They don't have a managed experience, but there are ways that you could use, for instance, the BigQuery connector to come from Spark and go through. And it can use, if you use the catalog, you can use other compute engines. But we'll talk about that in just a second. So you could use Spark, even though it's managed by BigQuery, yes. But we'll talk about what the implications are there. I think that's like the next to last slide explains that.
Jay, you're not sharing your screen.
I'm not sharing the screen anymore. Okay. All right. Select.
Does make looking at the slides somewhat harder.
Do you see it now?
Yep.
Okay. I probably hit a key. Again, I worked at Microsoft. You'd think I'd be better at using Teams in this, but anyhow.
Thank you.
All right, so single control plane. So we're down to 8 minutes, and I kind of want to get to the other gentleman's question with the last slides. I don't have too many more to go. These are sort of benefit slides. So I'm going to make the point, but I'm going to kind of go through these quickly. So stop me if you need me to stop. The goal of Big Lake is to give you sort of the single control plane. This is work in progress. I mean, lake houses are still sort of the new paradigm, as I said in the beginning. So there will be things that are coming out. We're going to point that out at the end, and I think that's actually going to answer that gentleman's question. But that's what we're looking for: Big Lake to be a single control plane for your lake house. And let's see, interoperability with all the engines. This is what I was referring to with the analytics lake house. So with the analytics lake house, when you come and bring your lake house there, and it is when you are using BigQuery to do the compute, really when you're using GCP, you'll have this capability. But we have AI built in. We have something called BQML. So you can train and run inferences right there inside of BigQuery. And so if you have that, that's a capability that you're getting because you're using BigQuery and you're using Big Lake. So we start, hence the name Analytics Warehouse or AI, Lakehouse or AI Lakehouse, because of the inherent AI capabilities that are not just in GCP, not just Vertex, which is our sort of umbrella term for all of our ML and AI capabilities, including Gemini and stuff like that, but built right into BigQuery itself, which we typically call BQML, the ability to train off data in a table. And that could be an open table format table, an Iceberg table. But then you're also getting the scale of BigQuery, which, again, it's serverless. It's like a microservice architecture. It's serverless. It's completely elastic. You don't ever have to worry about a VM. You don't have to worry about sizing things. I'm going to stop there because I figure quite a few of you are already familiar, at least with BigQuery. So, but that's, you want to think about that. You're building a lakehouse there, and you're getting these other capabilities of the massive scale of BigQuery plus the AI capabilities, hence the AI Analytics Lakehouse. And then the shared metastore, and we'll get to that in a second. So I'll skip on through that one. Just going to build the slide out here. This is just a component diagram representing the storage, the cloud storage, the Big Lake that manages all of it on top of that with the capabilities that you have. You have your engines, you have BigQuery and then Dataproc and all this that can go through. So I want to make it clear, it can access data that's in the metastore. What I was saying earlier is I don't believe it has a metastore of its own. Dataproc doesn't, but we'll pick that back up in a minute. And then the AI part on top, whether you're using BigQuery notebooks, you're using AI Workbench, you're building agents, LookML, stuff like that. We go through this really quickly but this is another interesting capability as you start using BigQuery. BigQuery has something called BQ Omni. So BQ Omni lets you build tables, originally external tables, now Big Lake tables. And so if they're open format, you're going to be able to build Big Lake Iceberg tables in other cloud providers. So you'll see the icons for S3 and for Azure's blob storage. So Omni lets you sort of do that. So now you're getting back to the single place, a single pane or single control plane to manage all your data, even if that data is sitting in storage in another provider. This is just showing the BigQuery Studio and how, okay, even in the studio experience, you see that you can have references to data sets that are included by Omni, Big Lake, or external tables sitting in cloud storage. They're all right there, so you can write queries and go against them. And then finally, this is sort of an architectural diagram of BigQuery with the native tables, and then the open lakehouse with the Iceberg tables. You have Big Lake Managed and Big Lake Iceberg. That's the remaining distinction I really want to make before we run out of time. Is on this slide, you have managed Big Lake tables, so managed Iceberg tables, and you have self-managed, which means you're taking care of, we're not doing the compaction, we're not doing all that stuff. They can still be in our catalog, but it's not managed by BigQuery. And then on the far right, you have the Iceberg tables that are in, this was the Omni thing on the previous slide, you can still have Iceberg tables that are in the other storage things. And then your choice of query engine. So let me go through this one and one more, and then we will we'll have a few minutes to talk. Big Lake table types. So you have self-managed Iceberg tables. Again, here, the naming convention is not what I would choose myself, but Big Lake Iceberg tables. These are self-managed tables. So this is where you're responsible for managing the tables, vacuuming, compaction, all that stuff. The reason they're called Big Lake Iceberg tables is they're still in the meta store so that you can use a common store. You have to use a catalog. And if you choose to do so, you can use the BigQuery meta store. So they're called Big Lake Iceberg tables for that reason. Second one is the managed one. This is the one where we will take on those operations for you. Compaction, vacuuming, the auto clustering, garbage collection. It'll all be done for you. It'll pick the optimal file size. More information on that is in the documentation, which is in the reference slide. And then external tables are maybe more what the gentleman was talking about. Big Lake external tables, those are the tables that just aren't in the meta store. We're not managing them. You can still access them from BigQuery because basically this is just it's like your traditional external table. And it can be an Iceberg table, but we aren't managing it. It's not in the BigQuery catalog. And so you basically have a definition so you know how to go out and get to the file. And then what I was saying that I think might answer what your questions were about Spark and that experience. On the roadmap, they're trying to get unified Iceberg tables. There's one point here that's crucial to understand. Today, when you have self-managed Iceberg tables, okay, this is when I'm going to call it a third-party engine, Spark or something other than BigQuery, is managing the table, and it can do writing. Those tables are typically are just read-only to BigQuery. You can read. When they're managed tables for BigQuery, then it's writable, but they'll be read to the other one. What unified Iceberg tables are trying to get to a point where you can have the combination of the two. You can create an update in both Spark, and you can create an update in both BigQuery. That's not exactly where we're at today. I don't have an ETA on when that's coming out. Maybe I'll find it out in the next, maybe I'll find it out today, because like I said, we have the engineering team talking to a lot of the customer engineering community about where this stuff is specifically on Lakehouse. And so the decision slide here that's kind of worth going through. Which cloud is your data in? GCP. Is it going to be an open data format? No, then just use native tables. That's just use regular BigQuery. If it needs to be, or you want it to be an open format, aka Iceberg, do you want us to manage it? Yes, that's the table you use. Big Lake Iceberg tables in BigQuery. If it's a customer, if you want to manage it yourself, then what type of rights, so on and so forth, it can come back this way. But most likely, if it's customer managed, then you're using that first one from the previous slide. Again, my apologies for the names because I think they're confusing, but use Big Lake Iceberg tables, which means you're managing them, but they're in our meta store. Let's see here. There's a little bit about pricing here, storage costs, the optimization costs money, but you can find all this online. So, and there is a link number 10 is where you go find out about pricing. Link number 1 is the blog. And the rest of them is really the documentation for creating them and understanding about the Big Lake meta store and all that stuff. Now, we're right at time. I can hang out I will send you the deck like I did last time. I can hang out for a few extra minutes if you guys can, if there's any questions I can answer or I can take back, especially if it's about like Spark and its interaction with it. But yeah, that's what I have for today.
Thank you.
Thank you.
Nice job, Jay.
Thanks, Norm. All right, well, if that's it, thank you for your time. Norm, Wei-Win, I'll see you guys tomorrow.
Thank you,
Okay.
Jim.
Thanks, everyone.
Thanks, everyone.
Slides
Thank
out.
you,
Have a
James.
good day.